G'day, it's Richard Marr from Mars Classes again, and today we're going to have a look at a very famous experiment that was done in history and led to the development of a law called Coulomb's law. The experiment was performed by Coulomb himself, and back in the day when he was working, there was no corner electrical store like a Tandy or something like that you could go down to and buy equipment to do your measurements and so on. He had to actually design and build the equipment he was using. So what he did was pretty cool. He designed stuff that looked at the force that would exist between charged particles. Because back in the day, they knew that like charges would repel and unlike charges would attract. This concept of charge, they really didn't understand what it was because they didn't know all of the subatomic particles, but they recognised that there was some intrinsic characteristic which would lead to repulsion and attraction. We now know that if you, say, rubbed a cat, the cat's fur, it may rub the electrons off the fur and the cat could become positively charged. It'd be a positively charged cation. And if you introduced another positively charged cation in proximity to it, they would repel. So we're aware of that sort of stuff nowadays, but back in his day, he didn't know to what degree the force would be. So he had to design some equipment and conducts lots of experiments and be meticulous with his measurements to come up with a relationship to determine how the force could be determined. So the equipment he used was similar to the one in the stamp, which I've just overlaid with a better diagram of it. Now, what it consists of is a number of two spheres, A and A dash, which are connected to a central wire. If the A and A dash apparatus rotated, due to a force being applied on them, they'd rotate through a certain angle. He brought up a charged rod to the part of the apparatus which I've labelled B, and when that charged rod came in contact with the rod that has B in it, B would also obtain a charge, and because it's in contact with A, that would obtain a charge, and they'd both be the same because they're in contact and the charge would spread evenly. So he recognised that there would be a force that existed between A and B which would cause A to rotate the central cable. So what he had to do was find out what that force and the amount of rotation has to do with the amount of charge. So he recognised that the charges on A and B could be determined in coulombs, we now call it, as the unit of charge. But QA and QB represent the charge on each of those spheres. But he had to calibrate his apparatus first. So what he did is he applied a force to A and determined through what angle that force would make the central cable rotate. Once he'd calibrated it, he could then go about bringing B up near to it with a similar charge and know the distance between A and B and know the charges on A and B. And then if he could measure the degree of angle that they went through, he'd know what force was applied. And the other thing he noticed, and if you can see the original location of A, the blue force vector is larger than the final location of A, which means the force at the final location is smaller than the force at the original location. He recognised that to be that the force was proportional to the inverse of the square of the distance. And he found that out through meticulous, as I said, measurements. After he did that, he thought he'd look at the amount of charge and what impact that had on the size of the force. So in this instance, what he did is he had an instance where he had double a charge on A that would be on B, and when he had a look at the impact that has, it went through a smaller angle because the charge was now smaller. So he found that the force is proportional to the product of the charges on each of the two objects. And combining those two equations, got the equation pretty similar to the one we now know as Coulomb's law, and that was that the force exerted between two charged particles is proportional to the product of the charges and divided by the square of the distance between them. Now, if it's going to be equivalent to, we have to multiply it by some constant. So again, through meticulous measurements, he found a value for this constant. Now, the constant came out to be a thing called 1 on 4 pi epsilon, where epsilon represented the permittivity of the material between, or the medium between the charges. Now, if it was free space, that permittivity is given a certain value. So when we're looking at the permittivity, it is describing how much electric field is generated per unit of charge in that medium. And when we look at free space or a vacuum, the value is approximately 8.85 by 10 to the negative 12 farads per metre. When you plug that into 1 or 4 pi epsilon, you get the value of 9 times 10 to the 9 Newton metre squared per Coulomb squared. Now, you notice that down the bottom I've put epsilon 0. That's the symbol we use for the permittivity of free space, or the permittivity of a vacuum. If it was wax, or if it was glass, or if it was steel, that would have a different value. Now, the other really cool or really neat thing about this I've alluded to in an earlier video about the gravitational fields is that if we look at that equation F equals K Q1 Q2 on R squared, and we compare that to the gravitational equation F equals K M1 M2 on R squared, you can see the similarity between the two, and that is remarkable because they're two of the fundamental forces, and yet they seem to follow the same relationship. Okay, so that's just a really quick video looking at Coulomb's law. In subsequent videos, we're going to have a look at some of the upshot of this law and some of the calculations and work we can now do nowadays, now that we know the stuff thanks to Coulomb himself. So until next time, I'll see you.